application when we went through because there wasn't enough time to do the whole thing. But anyway, we're going to do it today. And it's an algorithm. Now, some of you have seen a randomized algorithm in like your intro classes, maybe 125, maybe 225, or whichever equivalence you took, and it was randomized quicksort. Okay. This one is similar, but it's not often analyzed. It's done in my third year class, the Algorithms and Data Structures class 307, but that's probably a long ways off. Okay, so we're going to look at this problem, and it's finding the element of rank k. So k is one parameter in a list of n distinct values. This is maybe something you've never seen before, the notion of rank. Rank is just exactly what you think it sounds like. Like if you're ranked number 1, that means you're the first, among all your classmates. Say, if you're ranked number 2, you come second, rank 3 is third, and so on. Rank n is last. Okay, so if you imagine like you sorted the entire thing and read them out from first to last, 1 through n, the rank would be where they appear in a 1-indexed list. Okay, so rank 1 is smallest, 2 is second smallest, and so on, and rank n is the largest. Okay, so that's what rank means in this situation. Now, even more interesting is that, we study this in algorithms class. That's fine. That sounds very academic. This is also a LEC code problem. Some of you have heard of LEC code. How many of you use LEC code or have tried LEC code? That's like maybe 15 of you. That's pretty good. So there are a lot of problems there that are, and when I love LEC code, I pepper a whole bunch of LEC code problems into my advanced class, which I mentioned before. This one is LEC code number 215. And the interesting thing about this problem is that the comment section, people are very opinionated about their algorithm, why my algorithm is the best, and so on. Trying to pump themselves up, that's fine. But there are so many different solutions to this question that is actually interesting. There is a little bit of debate and valid debate about what is the best algorithm. I mentioned I teach this algorithm in 307. I actually ask this question routinely on a final exam, and I ask it in a different way, but I basically ask, find the element of rank k of an unsorted list. And they routinely, like maybe 80-85% of my class answers this algorithm, which is actually not best. Okay, it's probably the thing that you thought of. How would you find the element of rank k in an unsorted thing? Sort it, and then it's all in order, and then just pluck out the one that you want. That's indexing. That's order 1. Okay, so if you add up all the running times for this, okay, so that would be n log n for your best sorts, and index is 1. Okay, you add those two things together, and the n log n dominates. Okay, so just to write this down here, so the best sorting algorithms cost big O of n log n. Index is a single op. Okay, so it's random access to go to a memory location. Okay, and you combine these things together, and the total is n log n. And the question is, can you do better? And the answer is yes, you can. Otherwise, I wouldn't, talk about this problem in this way. Like, I assign it as a thing in 307. There's sort of an interesting algorithm where you can get this thing down. It's a randomized algorithm, as it turns out, that you can get this technique down to order n. Before I get to that, though, there are some other variations of this problem where it might make sense to sort. This is like this is sort of like a pre-processing step. Okay, where it might make sense to do that, and that is if the data structure doesn't change, if your array doesn't change over time, and you have like lots of queries, then maybe you sort it once and then all the queries become almost trivial from that point on. Okay, so you would have to do something a little bit more fancy than this. This is sorting every single time, but you could just have a tag. You could attach it to the data structure that says, am I sorted or am I not? And if you're not sorted, then you call sort, and then you index. And if you are sorted, then you skip the expensive sorting step and just index. Okay, so you could do that sort of thing. This happens a lot, like in the industry, if things are very lopsided, right? So if the update to selecting or indexing ratio is very small. Okay, so you could imagine like if there were maybe it's not worth writing this down. I'll just say it orally. So if you were to index many, many more times than the pre-processing step would cost, then maybe it's worth it. Okay, so say you were to pay n log n upfront once, and you had something that was much, much bigger than n log n. Okay, then that would be worth it, right? And you would actually have a win here. Doesn't work in general, but so this is what I'm saying. There's a lot of variations in the solution, a lot of debate. I encourage you to try the problem and submit your solution to LEC code and read the debate there. But we are going to do one particular algorithm, one solution, and it's a divide and conquer strategy. Okay, before I get into that, there was a hand that went up. Say it again. Yeah, so the thing about bucket sort, so I don't want to get into the details about the so-called order n sorts like bucket sort and counting sort. Bucket sort works in some very specific circumstances, I grant you, and even then it doesn't work all that great. So for example, so bucket sort is where you take like a number and you chop it up by its specific numbers. So you or a string and you say put all the A's into a bucket and B's into a bucket and then you sort those. It doesn't work for general sets. Okay, so it works sort of okay for numerical things and for strings, but it doesn't work in general. Yeah. So and even then, the analysis, it's maybe n and it's maybe not. Anyway, I'll leave this for your algorithms course, and login in general. Okay, I'm just going to close this door, because it's getting a little noisy here. Hi, I'm just going to... Come on. Oh boy, come here. There we go. Okay, changing a light bulb. Seemed worth it. All right. Divide and conquer. All right, what do? We pick a random pivot and we partition around that pivot. That partition function that I mentioned is exactly the same partition function that you saw when you did quicksort. Okay, so you put all the things on one side and you put that are less than p and put all the things on one side that are greater than p. And here it sort of looks like this. Unlike quicksort, you will only recurse on one side and not the other in this case. Okay, so we construct the sets left and right. And we can compute the rank of p because we know how many things are less than p. Why does that make sense? Well, if you know the things that are less than p, you know everybody that's ahead of you in the rank order, right? You know everyone that beat you. You know everyone that you're beating as well, but it's the ones that are beating you that matter, right? The ones that are ahead of you. Okay, so everyone that's ahead of you, it increases your rank by 1. Okay, so your rank, if you know the number of things that is in this set over here, it's actually equal to the size of that set plus 1. Okay, if that set is empty, then you're rank 1. That's cool. Anyway, then you do a comparison. Okay, so this is basically one comparison here. Okay, you compare k with r. If k equals r, then you found it. Congratulations, you found the element of rank r, it's p. Otherwise, you're going to recurse in one set or the other. If it happens that the thing you're looking for is of rank smaller than what you found, okay, then you go left. Okay, and you just search the set for the same rank that you were looking for. Otherwise, you go right, and you do the exact same algorithm, but you throw away all of these that are ahead of you, so the rank that you search for in the list that's over here is reduced by r. Okay, just to slide those ranks down by a chunk. Okay, let's do a small demonstration just to make sure we're all together. I brought only the finest technology for you. Okay, which rank should we search for? 3. All right, so we're looking for rank 3. Okay, so let's pick a random pivot. I pick this one. Okay, so we do whatever partition says that we do, if anything, and whatever partition function you choose to run. I like the one that slides things down. Okay, so everything is over here. Okay, so we compute the rank of 11. This rank, I shouldn't write on this. I need this piece of paper for later. That was really dumb. Oh well. Live and learn. We'll flip this over a little later. Anyway, the rank here is the size of the set plus 1, which is 8. Okay, so 3 compared to 8, it's less than 8, so we search the left side. Okay, so let's pick another random pivot. And again, we'll do our partition. Okay, so that's going to be the way it is. And we compare this rank. This is a rank 2, right? So 2 is less than 3, so we're going to search this bit here. Okay, but we're going to search for not the, we're going to look inside this list. It's going to be looking for the thing of rank 3 minus 2, which is 1. Okay, so this sublist, we look for rank 1 now. Yeah? Because we threw away these ones over here. Okay, we pick another random pivot. I'm always picking the first one. And we partition, it's done, and the rank happens to be equal to the one we're looking for. So 4 is the winner. Okay, I just tossed them on the page, but you'll notice that we only recurse in one direction, whereas quicksort would, sort each part, right? It would do the partition on both sides. Okay, so we're only going down one strand. We left this 2 abandoned. Anyway, the breakage was not great on each one here. Okay, so maybe it's not so easy to see, but it could be really good, just like in quicksort, or it could be really bad. Okay, any questions about how the algorithm works before we get into the analysis? Do you believe, I guess is the question. No question? You're good? Okay. Is it good? How many of you have seen this before? Okay, so it's new. I love new things, right? This is a fast algorithm, okay? This is the best algorithm, actually. So hopefully you like it. You like this? Yeah? Feel good? Okay. So, let's go back to the algorithm. have to do the analysis. So the analysis is the next thing. Okay, and we want to know the worst case running time. First, we need to judge what is costing us any sort of running time here. And we can pick anything as long as it's the dominant operation, and the thing that I want to pick is the number of comparisons. It's the same thing that we would pick in any sorting algorithm, is the number of comparisons. This was one comparison, maybe two if you squint really hard. And the other comparisons are actually in here. When you run partition, you compare each of the other elements, there are n minus one of them, with the pivot. Okay, so overall, the total running time for this bit here, without the recursive subcall, is n comparisons. Okay, so it costs you n. Okay, question number one. What's the worst case running time? What's the worst situation that you can see occur here? How can it go down where it's really bad? Okay, not him. Sorry. I appreciate you, but I want someone else in this case. What's the worst that can happen to you? Good, yeah. So you always pick the min or the max as a pivot. Okay, and that's really good if that happens to be the rank you're looking for, but usually it's not the one you're looking for, right? That's the worst. Okay, so, and that's the same worst case as in quicksort as well, right? So if the pivot is always the min or max. Okay, so what happens is you partition the list into the pivot followed by the rest of the items, and then you recurse on this bit, right? Okay, but that of course costs you n. Okay, well you recurse on this bit, so you find a new pivot, and the breakage is like this. Well, that costs you n minus 1. I'll do one more, and then you recurse, and the pivot is off by itself, and n minus 3. That costs you n minus 2. So if you're perpetually unlucky, we end up getting n plus n minus 1 plus n minus 2, and so on. Okay, and we know what that sums to, don't we? Okay, so the recursive case shrinks by 1. So the total cost is n plus n minus 1 plus n minus 2 plus 2 plus 1. Or if you don't like dot dot dot, that is the sum from I equals 1 to n of I. And we know what that equals, right? N times n plus 1 over 2, which is n squared. Okay, so that's an n squared algorithm in the worst case. It's really bad. Good news is it's going to be sorted at the end, but whatever. We weren't expecting it to be sorted. That wasn't the call that he made. Okay, that's worse than sorted index, right? Now you might think that the best case would be you have even breakage, like right down the middle, and you know, so that it can't get too bad no matter which way you go. Okay, so if the pivot is always the median, which is around here, then the picture that you get is similar, but the breakage is roughly n over 2 on each side. Okay, not exactly, it's like due to a rounding error, but it's basically n over 2 each side. And then, you know, half of this goes away, say. Okay, so your recursive subcall, and so you pay n, but your recursive subcall is, you know, half the size, roughly. Okay, so again, this is going to be like roughly n by a quarter. Okay, you pay roughly n by 2, but again, half of it disappears, right? And then the next call will pay n by 4, right? And then half of it disappears, and half of it disappears. Okay, so that's a really good case. So then the recursive case always shrinks by half. And the total cost here is a round, okay, so it's a round n plus n by 2 plus n by 4 plus n by 8 plus 2 plus 1. Right, subject to some rounding error. So just to get rid of that rounding error, we will write this as a sum of n divided by 2 to the I, where I goes from 0. And we might as well throw in the whole kitchen sink, because this thing converges even if it goes all the way up to infinity. We'll just add up the infinite sum. And what's this equal to? It's not 2 to the power n, sorry. What's the sum equal to? It's not n. You're getting warmer, though. Say it again? No. Not log n. Are there reasons for the answers you're giving me? I'm actually asking honestly here, like, is, like if you just ignore the n, this is 1 plus a half plus a quarter plus an eighth plus a 16th plus a 32nd plus a... It's not 2 to the power of n plus 1. It's not an exponential. N, you're getting closer. It's 2n. 1 plus a half plus a quarter plus an eighth plus, that converges to 2. Right? Geometric, I should have given a geometric series on the midterm. Yeah. How many of you studied that? How many of you memorized the formula and then I disappointed you? I'm very sorry. I'll try harder next time. Anyway, this is a geometric series, guys. Come on, this is true. For all the stabbing, this is a bunch of n's added together. 2 to the n doesn't make any sense, and neither does log n. I mean, come on, this is polynomial math. It can't be 2 to the n. Can't be. Anyway, so-called worst case is n squared. The so-called best case is order n. The average case is what we would like to solve. Okay, so we're going to solve this using expected value. Okay, so we're going to find the expected value of this algorithm, or at least a bound, and the bound will be linear. Okay, so here's the claim. The expected number of comparisons to run a randomized select on n elements is bounded above by 8n. Okay, that's the expectation. And we're going to prove this by induction, but in order to do that, we're going to first prove a lemma. A lemma is just a theorem that has one purpose in life, and that is to help prove another theorem, and that's it. Okay, and the lemma says the expected size of any recursive subcall is at most 7/8 n. Okay, it can be really bad, but on average, you're throwing away at least 1/8 of the list. Proof. Okay, first thing, we're going to define an event C that says that we're going to get a good breakage, okay, something that's roughly in the middle, and the terminology we use for data structures is that the pivot is centered. Okay, so I'm going to draw what I mean by centered. So if we have a list that looks like this, centered is going to mean that it's in the middle half. Okay, so centered is going to be from n over 4, 3n over 4, anywhere in that stretch. Okay, so it's between the rank n by 4, 3n by 4. There are some round off errors there, but that's fine. The probability of C is going to be taken to be a half, although we could just bound it above by a half, just to deal with the round off errors if we needed it. It's not a big deal. Okay, and there are two cases. Either you're in the C range or you're outside. You're outside is actually really bad, right? You could end up with a really bad split, but it happens at most half the time, and those things, when averaged out by these splits, turn out to give you something that's roughly 7/8 in expectation. Okay, but you have to take a weighted average of that, and we do that by using the law of total expectation. Okay, so if C happens, the worst that can happen to you is a subsearch that costs 3/4 of n. So that's the biggest piece you could possibly get. It could be better, but it's no worse than this. And if C doesn't happen, the largest is n minus 1. You throw away one thing in the worst case. And the weighted average of those two things is actually, that's n, basically, and that's 3/4 n. The average of those two things is 7/8 n. Okay, but we'll use the law of total expectation because we have the technology. Okay, so the expected size of the child is the expected size of the child given that C occurs, times the probability of C, plus the expected size of the child given that C doesn't occur, times the probability that C doesn't occur. And this is bounded above by 3/4 n. This one is bounded above by n just for simplicity. Okay, so this is less than or equal to 3n by 4 times a half for each of those pieces. And over here, it's n times a half. And you add those together, and you get 7/8 of n. Okay, good. All right. It's been a while since you've done an inductive proof, I bet. Yeah, no worries. Inductive proofs are like the easiest thing ever. You just follow You just follow the mechanics. That's all it is, right? All right. Write out what you're trying to prove, do the base case, do the inductive hypothesis, and relate the inductive step to the inductive hypothesis. Okay, let's prove the claim. The claim, we're going to prove by induction on N. Just to remind you what we're asked to prove, it's going to be the statement. So the statement, this is not a step, okay? The statement we're trying to prove is that the expected number of comparisons is less than or equal to 8n. Okay, so this is not a step. Okay, I'm just saying what it is. Okay, so we'll prove this for, well, maybe we'll just say this is like something of n, right? S of n, the expected number of comparisons on an element list. Okay, so if n equals 1, then there's nothing to do. Then we require one comparison, which is less than 8 times 1 comparisons. Okay, so that works. And then we write down our inductive hypothesis, okay, which is we assume true for all smaller k. So the expected number of comparisons for size k array is less than or equal to 8k. And then we would like to show that the expected number of comparisons for the larger array, the n array, is less than or equal to 8n. And if we do that, we're good. We have to use this. That's the way the mechanics work. Okay, so the inductive step is the expected number of comparisons for size n array. And we would like this to be less than or equal to 8n. Okay, I'll give you just a moment to catch up. I know I've been writing a lot. Okay, the cost for a size n array is n comparisons for sure, because you have to partition it and compare, right? So there's n things to do, plus you have to do the recursive subcall. Okay, so plus the total cost for the recursive subcall. Okay, and that's it. That's all there is in terms of comparisons. So whatever this number of comparisons for size n array is broken up into these two components. And because we're using addition, we can use linearity at this point and pull the n outside. So it's n plus the expected number of comparisons for recursive subcall. Okay, and that number of comparisons, or this recursive subcall, I guess, is smaller than n, right? We throw at least one thing away. So the inductive hypothesis is going to apply. Whatever that k value is, it's going to apply here. And it says that whatever this value is, let's just call it k, it's going to be less than or equal to 8k, basically. Okay, so this is less than or equal to n plus 8 times the expected size of the child, whatever that is, k. Okay, so this is from our inductive hypothesis. And the expected size of the child is less than or equal to 7/8n. And the 8's cancel out, and we end up with n plus 7n, which is 8n. Nice. Okay, so this is a randomized algorithm that works much faster than sorting on average. Okay, add it to your war chest. If you happen to take 307 from me down the line, remember this. I ask questions about it on exams, but also it's if you want to impress somebody on LEC code, this is the way to do it. Any questions about this? Cool? Yeah? Does the randomized step have to be there? Yeah, so if you always pick the first index, then you're subject to whatever order things come in. And oftentimes, I don't know about your arrays, but oftentimes my arrays are, sorted or mostly sorted. And if they're in that order, you're screwed, right? Like you're in a worst case scenario. Sorry? Yeah, it's the same reason you pick a random pivot and quicksort. Yeah, same idea. Yeah, the randomization helps you. Yeah. Yeah. Interesting thing about quicksort is that the same as picking a random pivot is the same as scrambling up the array to begin with. So you can actually, it seems counterintuitive, but you can randomize the array, and that will make your algorithm tend to run faster. It's kind of funny. Well, anyway, funny irony rather than funny haha, I guess. Okay, good. All right. We have 3 distributions to compute the variance for. Might as well start here. Let's start here. Okay, binomial distribution. Compute the variance for this. Okay, so binomial random variable r equals the total number of successes in n independent trials. Okay, you could do the base calculation of this, right? Or you could use the shortcut, right, and just take variance of r squared, right? So, variance would be expected value of r squared minus the expected value of r, which is np all squared, right? And that would be the sum from k equals 0 to n of, I guess it's k squared, right? That's the thing that we weighted by, k squared times n choose k, p to the k and 1 minus p to the n minus k. You can do this. You shouldn't, but you can do this. I mentioned putting factors in front of this, and you can get this k to come down by taking this and taking the derivative, and then you can do a little bit more munging and then take another derivative and end up getting this thing to work out. You shouldn't do this, okay? Instead, you should take advantage of the theorems that we proved. And just to remind you, independence is a good thing. And you should take advantage of independence whenever possible. Okay, so here's what I mean. If you let I be the result of the ith trial, then R, this binomial, is equal to R1 plus R2 plus Rn. And they're independent trials. So you can use the theorem that we proved last time. Okay, so the variance of R is equal to the variance of R1 plus R2 plus Rn. And independence means that these variances just add together. Okay, this is the variance of R1 plus the variance of R2 plus the variance of Rn. And each one of these is a Bernoulli trial, right? What's the variance of Ri? What's the variance of Ri? Good. Okay, so p times 1 minus p. P times 1 minus p. And there are n of them, so this is n, p1 minus p. Geometric. Geometric, I'll make the same comment. Like, if you needed the expectation of, this r squared thing. This r squared thing is the sum of, k is equal to 1 to infinity, I guess, because it's unbounded anyway. It's k squared, and then we multiply by the probability of each of these, right? So k minus 1 times p. And this is like the arithmetico-geometric series that we did before. We could do some subtractions to try and whittle down this thing. Maybe there's another differentiation trick that somebody pointed out. There probably is a nice way of getting this to work out. We're not going to do that. Okay, we're going to take a small shortcut. Okay, so just to remind you what the tree looks like. This is what the tree looks like. Okay, R. Okay, maybe dot 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 is good at some point. Okay, so R. R is this tree, 1, 2, 3, 4, 5, and so on. And we're interested in R squared. R squared is 1, 4, 9, 16, and so on. Okay, and the trick that I did last time when I said we can use recursion is the trick we're going to use this time, except the numbers on R squared are not self-similar or as easily self-similar as they were when we did just the expected value. Okay, but we can handle it. Let A be the event. The first toss is heads. Okay, A is, this branch, and A bar is this subtree. It's maybe not easy to see that bar there, but there's a bar there. And by the law of total expectation, the expected value of r squared equals the expected value of r squared given A times the probability of A plus the expected value of r squared given A bar times the probability of A bar. We're going to find each of these quantities. Okay, we'll do the easy stuff first. Probability of A and probability of A bar. Okay, so that's P and 1 minus P. That's easy. Okay. The expectation of r squared if the first tosses heads is what? What's the expectation if the first tosses heads? It's 1. Why? Because it's over, right? It's over. It only goes here. It's a dead end. It's always 1. If you toss heads, it's done. There's no variation. It's 1. The expectation of r squared if the first toss is tails is this tree. And if you look at what the values are in relation to r, r has gone up by 1 because you're 1 level lower, and you square the value. Okay, so essentially the value in this subtree is r plus 1 squared. So this, when we take the expectation of that, is going to be the expectation of r plus 1 all squared. Okay, we've got 2 minutes. We can do it, I believe. 1 times p, p. Let's expand the bracket inside there. So expectation of r squared plus 2r plus 1 times 1 minus p. And if we sort of do linearity and expand this over 1 minus p, here's what we get. We get 7 terms. Okay, expectation of r squared plus, so we multiply by 1, so this is 2 expectation of r, and expectation of 1 is just 1. So that's if we multiply by 1. And we'll take this and multiply it by minus p. So minus p expectation of r squared minus 2p expectation of r minus p. Okay, this thing followed our way down here. Sorry, I used the big thick one because I was excited, but oh well, what can you do? Okay, so those go away. P and minus p, they subtract out. Okay, and we want to solve for e of r squared, right? So we'll toss this onto the other side. And then we'll collect whatever's left on this side, so we end up with 2 e of r, so 2 e of r. It looks like it's 1 minus p. We factor those two, plus this.